Komachi Raju, and this is the tech demo number 2 for Multivariable Calculus 2550, summer 2025. So here today we're going to be completing these 3 tasks using GeoGebra graphing calculator. So the first task is to graph this function, which is f of xy equals 1/2 x to the third minus y cubed plus 4xy, and then also to choose an appropriate viewing window. So here, let's go ahead and graph that using the using the 3D calculator. Here we have a 3D plot. Here's the the y-axis in green, the x-axis in red, and the z-axis in blue. So what you do is go ahead and type in your function. Alright, so you type in your function and press enter. And here we can see part of it, but it looks like it's being cut off. And this is because the viewing area is not large enough. So in order to fix that, we would just go to settings, and then here under basic, we can actually, let's tighten these up a bit. So x min is -3 and x max is 3. Same thing for y min and max. And then for z min and max, we're going to actually make that bigger. So -50 and 50. And then we actually end up seeing a more complete picture of it. And let's just ensure that we have typed this in correctly. Yeah, there was one small mistake. It's actually x cubed. Okay, so so this is the graph. So as you can see, it's kind of like a hyperboloid of some sort. There's some twisting going on, some very interesting features here. So it kind of curves down and up right here, but then here we can actually see it slopes down from this perspective. Again, this is the z-axis, up and down right here. But yeah, that's how you would graph this using GeoGebra, and you would change the viewing window so you can see a complete picture of the graph. Alright, let's move on to task number 2. So task 2 is to create a contour plot for the function that we just graphed, and it should also have an appropriate viewing window, and then also to color code the labels, and it should contain at least 6 curves with appropriate z values. So in order to do that, so a contour plot is 2D, so we're actually going to be switching to the GeoGebra 2D graphing calculator, which we have pulled up right here. And so as the instructions mention, a contour plot, it's just a series of curves where one of the variables, in this case x or z, is going to remain constant, and x and y will be changing. That's why it's in 2D. So in order to do this, the instructions ask for 6 curves, so we only have to plot 6. So I actually have the curves already typed up right here, and you just have to type each one into GeoGebra. So we can go ahead and do it manually the first time. So again, we're just gonna so first of all, let's label the curves, each one. So I'm just gonna label this first one as C1, and we can go ahead and type in our function from before. So that was 1/2 x to the x cubed minus y cubed plus 4xy, and again we're going to make that equal to -20. Alright, and press enter. Alright, so you can see here, so this was our function from before, but we just made the z value equal to negative 20, and only x and y are changing. And so this is our first curve. And so we just need to do that for curves 2 through 6. So I actually have them typed out right here, so we can go ahead and copy and paste them. And all we're changing are what x is equal to. So then the first one, x is equal to negative 20, and this one, x will be equal to negative 10. And the next one, x is going to be equal to negative 5. And again, I just chose these numbers just to get a complete picture and have appropriately spaced out intervals between the curves. But you can choose really any numbers. But if you make them too close together, of course, the curves won't show you that much unless you have many, many curves, and this assignment only asks for 6. So, alright, this is going to be when z equals 0. Alright. And then when z equals 5. And then this is when z equals, this is supposed to be a 10. When z equals 10. And again, after you type each one, you would just press enter. Alright. So see, and GeoGebra actually does this for us. It actually color codes each curve for us, but we also put a label on them. So as you can see in this graph, if you move the graph up, you'll see these labels move with the line. So yeah, we can take a look at this graph, this contour plot. So as we can see, it's the space in between the lines is actually getting closer and closer together right here. That's indicating that the slope is increasing. We also see that when z equals 0, it kind of changes shape, right? That indicates that there's some sort of saddle point at z equals 0, which essentially it's just a point in which the graph, or when our 3D object, I guess you would call it, has some sort of special point, I guess it is. So when z equals 0, you can see that right here on this graph. Our contour plot shows x and y change shape. So that's also a special feature of this graph. So yeah, this is our contour plot. Again, you can change the viewing window like we did before. You can also zoom in and out manually if that makes more sense to you. But yeah, really the viewing window is, I would say, from x equals 5 to x equals negative 5, and probably from y equals negative 4 to y equals 4. That would be a good viewing window for this contour plot. Because the rest of it, of course, it goes on for infinity, and you can see it converges here. Nothing really interesting happens that we know of. Alright, so that's task number 2. That's our contour plot. Alright, so now we're going to move on to our final task today, which is task number 3, which is graph the tangent plane to f of xy at the point 2, -1, and -3. And we're also going to show that the plane is in fact tangent to the surface at that particular point. So going back to this, let's go ahead and graph our point, which is, so you can do any point, usually that's a capital letter. You can do a equals 2, -1, -3, which is our point, and press enter, and GeoGebra will add a point on our curve here, and it labeled it A right there. So that's our point. And so in order to find the surface, that is tangent to this object at this point. What we would do is we would take partial derivatives of x and y, and essentially plug in that point to find the plane that is tangent at that point. So I went ahead and already did that. So the tangent plane is actually going to be z equals 2x plus 5y minus 2. So we can go ahead and just type that right into GeoGebra. Alright, so as you can see here, it creates this blue looking plane, this flat surface, and that is going to be the point that is tangent to this. You can see it goes right through A. That's A right there, our point before, which is 2, -1, -3. This plane goes right through that point, and it's tangent to the object at that point. So at that point, it just touches the object right here. So it's a tangent to the object at that point. And that's how you would graph it using GeoGebra. It's a pretty easy to do. Actually fun to see sometimes what unexpected shape these abstract numbers can take. Yeah, and so that is tech demo number 2. And those are the 3 tasks completed. So thank you.